Hello. Good afternoon, everyone. Okay. All right. Welcome, everyone. Good afternoon. Today, we're going to continue working on um, uh, applications of linear systems, 2x2 equations. And so hopefully at this point, you already feel pretty comfortable using elimination, using substitution. And so you'll see that the math part of this is actually something that I think most people feel pretty comfortable with. Uh, uh, what we're going to work on now is really boils down to setting up word problems, like a little bit like we did with the diagnostic test. Using uh, the wording in the question to set up um, a really clear set of equations, and then using the 2x2 like approach of either substitution or elimination, either one, uh, to to solve the overall system. So the um, uh, the idea I want you to have moving forward for today's class and really for the stuff on the midterm is that you know the math for this. If you feel comfortable with the examples that we did with elimination and substitution, and you know kind of what it means for them to have infinitely many solutions and stuff like that's all the math behind it. What we're going to do today with the word problems, the math is already done. It's more about really translating from English to a math equation, which is also a type of math, and it's a very important type of math. But it's not like you're really uh, solving doing some sort of advanced solving techniques. So let's get right to it. So let me see here. Okay. So yeah, this is going to be 8.3, and I'm going to post some more examples later. And we'll just try to do a bunch of questions from 8.3. So I think this class and the next class, we're going to work on solving. So let's say setting up and solving word problems that involve a system of equations. Okay. So here's the first example. So example. So the surf team at Mesa can take classes. So the entire surf team, like all the students cumulatively, can take classes that are 3 or 4 credits. Oh, not credit. So if the total classes enrolled in was 20, and total credits was 68. So 30. How many 3-credit courses did they take? Oh, all right. So I'm just going to read this over one more time. Example 1, the surf team at Mesa can take classes that are either 3 or 4 credits. If the total classes enrolled was 20 and the total credits, cumulative credits, was 68, how many 3-credit courses were taken? And what I care about when you're doing these problems is not so much like doing all the algebra correctly. I mean, that's very important, and I will like to see that. But what I really want you to show your work on is defining your variables. So we're going to always follow these steps. Step 1, and to get full credit, you need to do these on the test, even if it seems a little bit tedious, but it's very, very important. And you'll see later some slightly more confusing wording where this process really helps. So clearly define your variables, almost to the point of like being overly detailed. And then step 2 is write super clear equations. Or maybe I'll say write and title and give them a title. So clear enough that you can give them a title, and the equations that you write down, there should be so clear that once you read your definition of the variables and the problem, you'll be like, oh yeah, that equation makes sense. And step 3 is the actual one to solve with algebra. Solve with algebra. And I'll put maybe step 4 here is to check. Check and do a common, do a insanity check. Like, does this answer make sense? So plug in or ask yourself, is it reasonable? Plug in or is it reasonable? Okay, so I'd like for you guys to try this for a little bit on your own. Message me if you're totally stuck, you don't know where to start at all. But I do want you to I do want you to message me not the answer, but the after you've defined your variables, what would you write down for the equations that are required here? And if you're not sure what are some good variables or where to even start, also message me. I'll message you back a hint. So a lot of students, about 8 students messaged me for a hint. Not sure where to start, which is great. Nice. And I'm seeing, so my response to those students in the very beginning is focus on what don't we know? That might help you to answer part 1. So really focus clearly on what is the quantity that we don't actually know, or quantities, because remember there's might be several unknowns that we're working with because this is a system of equations. So there might be multiple things that are unknown here. Awesome. I'm getting a lot of good responses, so just bear with me if I don't get back to you right away. Or if I forget to get back to you, please just message me again in a few minutes. And the key is to be as precise as possible about what you don't know. And when we define variables, we can write like, x equals or y equals something. And you don't have to write an equation. It doesn't need to be, for number one, it doesn't need to be an equation at all. It could be a sentence. It could be an idea that represents something. When you write math equations, you usually like you try to do algebra and write like, some sort of expression. But in the very beginning, when you're defining variables, I recommend just using a phrase that represents something. Try to be as precise as possible as to what is actually unknown in this problem. Nice. I'm really happy. A lot of students are like, after like, if you read it at first, like I have no idea how to do this, then kind of read it again, thinking about it a little bit over, and then I see a lot of people are perfectly thinking about, okay, what is the actual unknown? Um, the hardest part is figuring out like what is actually unknown and how to precisely say what it is. Then once you have that, the equation part should be something that's like very, very obvious. Like you once you see it, once you write it down, you're like, you can explain to somebody else, oh, you don't need to solve anything. You just say, okay, this equation explains this, and this equation describes this thing. This equation represents this idea or this quantity, and another equation represents another piece of information that was given. So I'm going to give some students a few more minutes to think about it. I'm really happy that you guys are engaging and trying to actually like not just wait for me to give you the answer, but I think it's pretty awesome that you're working on a problem that you haven't seen before, maybe don't quite know how to do it, and you're making progress. That's what math is really about. So I'm seeing a lot of students are now have set up the unknowns correctly. When you're not sure about what the equation should be, ask yourself, hey, can I explain why it's this equation, what it represents, if somebody challenges me? And once you kind of have that mentality, like I need to justify this to somebody else, and really you're justifying it to yourself so that you know it's correct. Um, okay, and those of you who got the equations, make sure to solve. Okay, and now Lupe, yeah, go for it. So please tell us, what were your variables that you used?
So on the top equation, I did two equations, right? So I did y plus x is equal to 20, and then I did 3y plus 4x is equal to 68.
Nice. So y, let's do x plus y
Yeah, we
is
did
equal
that.
to 20, and 3x. But before you even do that, and this is kind of very important to get full credit, what was the explanation for what x and y represent? Like you can use an English
Okay,
sentence also.
so x and y represent the amount of times each course was taken.
Nice. So x would be, let's say, In this case, it would be what? The number of,
The number of classes, the number of times you took the 3 credit class.
perfect, nice. So number of 3 credit courses. And a lot of times students who are not too familiar or like maybe rushing a little bit, I see a lot of times, and I even saw a few times in our class, people will just write x equals 3. And that's super, super confusing if you're trying to do a more complicated problem, because x doesn't equal 3. X equals the number of 3 credit courses. And just write a full sentence. That's totally okay. And a lot of times you'll see that the things that are unknown are something specific about some quantity. And it's okay to just write it out. It takes like maybe a minute or something, but just write it out so that you're clear on what it is and the reader is also clear. And y would be the number of 4 credit courses. So to me, this is maybe half of the battle, maybe even 75% of the battle. So this is really important. This is step 1. All right. And so, Louis, what do your equations, now that you got those variables, how can you justify your equations? How would you title them?
What do you mean?
Like the first equation, what does it represent? What is it saying as a sentence?
The amount, the total amount of classes was 20 that were
Nice.
taken.
Nice. Excellent. And then what does the second equation represent?
The amount of credits earned.
Excellent. And do you feel like once you had your variables set up, do you feel like you could justify that those are the correct equations without doing too much work? Or
Yeah.
It's pretty clear, right?
Yeah.
Good. That's how it should always feel like when you're writing these things down. It shouldn't be like something complicated that you need to solve. You're actually not solving anything. You're just expressing some information that you're given, and you're writing it down using some math. That's it. The next step is solving. But we haven't even solved anything yet. We're just setting it up. So this is total classes. I don't like that color. Let's do a different green. This is total classes. And this is total credits. Awesome. And what you'll see as we do more of these is a lot of these types of questions, they don't, one of the first examples we saw, I think, was like, maybe, was it hot dogs and hamburgers or something at different prices, and we're talking about revenue. Usually you see things about like the total quantity of things. This is a type of problem where you have like a total quantity of something. And then each item that you are talking about has another like price or credits or something, and then you have another like total price or total credits of all of the things combined. So that's a common type of problem that you see here. Okay, so now from here, Lupe, which approach would you use to solve?
Well, I use the process of elimination.
Nice. So did you multiply the first equation by negative?
By negative. Well, since mine was flipped, I did -4, but yeah, -3 works as well.
Okay, yeah, -4. Actually, this is a good point. When you're solving this, and this is not so important for our class because, I'll check all your work and I'll make sure that you're, if you got all the right steps, if you mess up at the very end, you'll get mostly full credit. But like on the SAT, one really kind of messed up thing that they do. Does anyone want to like share what they think that? Does anyone have an idea what's something that they can ask on the SAT, or like an answer choice that they could include that would mess people up?
0.
What was that?
Maybe they could put it out of order.
Yeah. So yeah, they can ask like there's there's 2 unknowns here, and we know how to solve for both of them, but you have to read carefully which unknown we want to solve for. So here we actually want to get x. Lupe was right. It's better to get rid of the y, and then you can solve directly for x. And if you need to, you can plug back in and get y, but you don't even need to in this case. So there's a trap there that like there's two answers, and they if you're not careful which one they're asking for, it's really easy to solve for it and then say, oh, okay, I see that answer, and then just move on. So let's solve for this. So multiply by, let's say, -4, like Lupe suggested. So this would be minus 4x minus 4y equals minus 80. Combine everything, and we get these cancel. We get negative x equals negative 12, or in other words, x is equal to 12. And plugging that back in, we also get, therefore, y is equal to 8. And the answer that we want is actually this one. But, you know, to kind of trip people up and make sure that you're reading the question carefully, sometimes multiple choice answer tests will have 8 as an answer as well. And that's really, you know, unfortunate. If you eliminated the x first and you got y, then maybe you would get tricked on that. Okay. Let me see here. Please hit the yes button if you feel now pretty comfortable with this example. And also, are there any questions? So one student asked here with the 3 and -4. Oh, I did. So one student asked, why didn't I do anything with the 3x and -4x? I did. I just kind of wrote it funny. I moved, these go to 0, this is 0, and this is 3x minus 4x is negative x. So I just kind of moved it all to one side, or moved it all, like I got rid of the 0. Okay. Any other questions about this example? And let me just see here, participants. Cool. All right. Looks like a lot of students feel pretty good about this one. Let me ask. There's kind of another way to solve this one. That's nice to see. Now that you've seen, I would like for you to solve all of these, trying to set it up with the system. But sometimes there's little shortcuts that you can use to solve it without like doing any too much advanced algebra. Does anyone see another way you can solve this one?
I mean, you could just guess and check, which is what I did initially. But
oh, okay, that's good. So guess and check. What if you thought about like kind of the worst case scenario, like and this is kind of like guess and check, Lupe. What is kind of the one possible answer that wouldn't work? But like would have the most number of, let's say, 4 credit classes. What would happen if we took all 4 credit classes? If we took all 4 credit classes, or if the surf team took only 4 credit classes, then how many credits would they have total? They'd have 80 credits, right? Not 68. So what happens every time that they take, instead of doing a 4 credit class, they take a 3 credit class? What's happening to their total number of credits? It's going down. By how much? Every time they switch out a 3 credit course for a 4 credit course, how much is it dropping? Just by 1. So if we know that the total number of credits that they took is 68, how many times do they have to swap out from an all 4 credit course like enrollment? How many times do they have to swap it out for a 3 credit course? To get from 80 down to 68, how many do you need to subtract? It's 12. So if you take away 12 of the 4 credit courses, you're left with, and you turn those into 3 credit courses, but you keep the rest of them as 4 credit courses, you can argue that, oh yeah, that'll leave you with 68 total credits because you're going 12 down from 80. And then you're still going to have a total of 20 classes. So it's another way to think about it. You can try to apply that idea to several of these problems, but and what's really happening there, if you think about it, is really just substitution, and you're just solving a nice substitution expression. Yeah, let's continue. Let's see what else we got here. Okay. And so let's do another type of problem. This is a mixture problem. Okay. I don't know if you guys have ever been to this tea place on Convoy, but it's a pretty nice one. I think it's Kung Fu Tea. Sells oolong. And by the way, these examples, if you want to read more examples, these examples are all similar to examples in the book. But I'm just doing them with slightly easier numbers because we won't have a calculator. So I'm just trying to make the numbers a little bit nicer. I don't know why I make that. Ooh. So Kung Fu Tea sells oolong tea for $5 per pound. And what's another tea? You guys want to message me? Somebody want to message me a type of tea that they like?
Green.
Green? Great. Oolong tea for $5 a pound. And green tea. Green tea. For $7 a pound. They want to make a blend of 10 pounds that sells for see here. Sells for sorry. $5.40. How? Oh, sorry. So $540.40. Per pound. And instead of a 10-pound blend, I'm going to make it a 20-pound blend. That sells for $5.40 a pound. The question is, how much or how many pounds of each tea should be in the blend? Oh, taro, chai. Okay, those are good. Maybe for future examples, I will use those. I like that. So again, let's do steps 1, which is define the variables. Steps 2, what are your equations? And this one seems a little bit more involved than the last one, but you'll see it has some very strong similarities to it. And don't jump to the solving. Just message me once you've gotten your variables defined, and you have your equations defined as well. And then I'll kind of give you a hint on how to solve it without using a calculator. And there is something slightly tricky with this one. But otherwise, it's very, very similar to the example that we just did. Wow, you guys are doing awesome, by the way. Um, So I'm just helping students. I saw a few people got the right setup, and some people solved it. About half of students are very close. Um, okay, let me see here. So, so let me see if I could ask. Okay, so let's see. Let me see here. I want to ask. Okay, Anaya's going to share with us the variables that she got. Go ahead, Anaya.
So for
Anaya, I'm sorry, it's breaking up quite a bit. But I'll share with the students, or you could try again if you hit the space bar. I'll share with the students what your idea was. So Anaya wrote to me that she set up x is equal to the number of pounds or quantity of oolong tea. And this is really important. You don't want to just write x equals $5 because that doesn't help you solve anything. If x equals 5, that's the answer. $5 per pound is an important fact about the oolong tea, but that's not the actual unknown. And then you want to try again for y or it might be my connection as well. I'm not sure. And so for y, it would be the number of pounds or the quantity of number of pounds of green tea. Sometimes you can use different letters, like you could maybe use, don't use O because that would look like 0, but you could use maybe T and G for oolong tea and green tea. You can use X and Y, whatever you feel comfortable with. Okay, now a lot of students here came up with two very, very good equations. About half of the students came up with two excellent equations. And then when I kind of mentioned there was a mistake, students tried to switch them up, even though your original equations made a lot of sense. So always, just because something might be off doesn't mean that you have to change something that does make sense. Try to think about, okay, where did I do something that wasn't justified? And trust in, if you ever do something that you really believe is correct, stick with it. It's good, even if it's wrong. If you feel like you can justify that and you're confident in it, you don't just have to switch it because it might not be exactly correct. So one thing that a lot of students wrote down next was, okay, they wrote x plus y equals 20, because this is the total pounds. This is the total pounds. And then a lot of students wrote 5x, because $5 per pound, plus 7y is equal to 5.4. Okay, so this is a very common thing to write, and it looks very similar to the last equation. Can anyone volunteer or anyone message me in chat? I'd like to have somebody volunteer for me, for us. Can you fix this last equation? And
I can.
Go ahead.
So I had written that equation too, and then you told me it was wrong. So I realized what I did. 540 is per pound, but since it's 20 pounds, you have to multiply 540 by 20, which is 113.
Excellent. Thank you, Amy. And so what would be the title? Instead of total pounds, what would be a good title for this second equation?
The total cost of the coffee or tea, sorry.
exactly. It's the total cost of the package or whatever, the blend. Awesome. And this is a really easy mistake to make. And this is kind of what's hard about these problems is just being careful with the setup and you know, being aware of these little details. And this is a really common thing about mixture problems in particular, where they give you some like amount of two different rates of like how much things cost, or maybe how much concentration they have, some sort of uniform rate, and then they ask you to combine them to get like a desired rate. But you have to remember that the last equation you're going to use will be a total cost. Okay, so Amy did a good job there. You multiplied 54 times 2 to get, what was it? Is it 54? Is it 108? Or one?
I think it's 113, but I might be wrong.
Well, if you do 54 times 2, it's going to be 108. So I believe it should be $10.80. Is that? But regardless, let me show you how you can do this without worrying too much about the actual multiplication. There's a little trick here that you can do, and this is going to be important because on the test you're not going to have a calculator. So the trick with these is don't actually do the multiplication. If you just saw a random problem like this in a book, yes, set it up and use your calculator and then try to solve your system. But on our tests, I'll show you a nice way to do it because I'll always make the numbers pretty nice for X and Y. So if we try to do elimination, and let's try to figure out, let's try to eliminate X. So if we multiply everything by -5, you get minus 5x minus 5y equals minus 5 times 20. And I'm not even multiplying through the minus 5 times the 20. Now, do you guys see what I'm going to get on the left side? The 5x's will cancel, and I'll be just left with 2y is equal to, and one nice thing you can do when you're trying to like avoid doing a lot of math and you see the same number show up is you can sort of do the distributive property, right? You can treat the 20 almost as if it's a variable. So what's $5.40 minus $5? You're just left with 0.4 times 20. And now, dividing everything by 2, you're left with y is equal to 0.4 times 10, which would just be 4. Plugging back into the first equation, you get x is equal to 16. And you could have done it, you could have just also multiplied. You don't need to do this little trick. This little trick just helps you to avoid doing a lot of arithmetic because you're going to treat the total number of pounds almost like a variable, and you never multiply it until the very end because you try to simplify as much as you can before you start multiplying. So that sometimes helps with these problems. But if you just multiplied it through and you made it 108, and then you subtracted, you got 2y equals 8, then you get y equals 4. That's also a good approach. Let's just think about this for a second. Do you guys think that this makes sense? Why should there be a lot more of the oolong tea than the green tea? Can anyone explain like why that seems reasonable? Nice. Yeah, Archer and Conchita, very good. Yeah, the total blend is cost the mix the price for the mixed blend is really close to $5. So you'd probably want to have more of the cheaper tea than you have of the expensive tea. If it was straight up like in the middle, like of the two prices, if it was $6 per pound, then you know you would have half and half be the green tea and half be the oolong tea. But because it's closer in price to the oolong, you want to have more of the oolong. And in fact, what's really happening here is this is a weighted average, and it's not a coincidence that 16 to 4 is in a ratio of 4 to 1, and if you look at the kind of how the pricing works from $5 to $7 is overall $2. So 40 cents is 1 unit. 40 cents is 40 cents away from $5, but you're also $1.60 away from $7. So you're $1.60 to the left of $7. So those are in a ratio of 4 to 1. So it's not a coincidence that our answer is also in a ratio of 4 to 1. And I'll kind of do another explanation of that, show you guys that another time. So one student asked, why do we multiply by 20? So you multiply this equation by 20. This is really important because the $5.40 is the money per pound. So that's not the total cost. The expression on the left, $5 per pound times the number of pounds of oolong, that's how much the oolong tea costs, the entire amount of it. And the 7y is the total cost of the green tea. So combining, you need to multiply by the total cost of the entire blend. Okay. And exactly, yes, the final answer would be X is 16 pounds of oolong and 4 pounds of green tea. Excellent. Please hit yes if you are comfortable now with this example. You feel like you see the difference between the last example, that they're very similar. And you feel confident in setting them up. Like if you make a slight mistake in one little detail, it's not the end of the world. Don't just change your answer and all your justifications just because there might be some slight error. And also, any last questions here? Okay, let's. So I'm not going to do. I encourage you to read example 4 and example 5. Let me see here. Yeah, example 4 and 5 in the book. We might do something similar later. Let's move on just to introduce. Oh, how do I know what to put on the third part? I didn't. So, Amy, what did you mean by that? Oh, this thing. Yes. So, how did I get the third equation here? I just choose to do elimination. I chose to eliminate the x. So I multiply the entire top equation by -5. You could do, if you wanted to, you could also have done multiplied everything by -7. But I in particular chose -5 because $5.40 is close to -5. So I knew that that's going to cancel out and be really simple to work with. If you chose to do the 7, you would just have to do 540 minus 7, which is also not too bad. Okay, so let's, I want to do example 6 and 7. I'm not sure if we'll have time to finish them. We'll do some more tomorrow, and or we'll do some more on Thursday. So let's go to the next one. And we've already talked about this. Famous, this is going to be famous dirt problems. So DIRT stands for distance, and some of you might have heard it. I actually learned it from students, I think at La Jolla High or something, and also in Claremont High. I like the DIRT equation. It stands for distance equals rate times time. And it's a specific case of the work equals rate times time equation. And this is a pretty nice intuitive equation if you think about like traveling along a highway at a certain speed, like if you're going 20 miles per hour. If you're traveling at 20 miles per hour and you travel for 3 hours, then your distance traveled is 60 miles. Okay. So we're going to use this equation to solve problems that involve two moving objects or two different trips. And what we're going to set up is we're just going to set up two separate DIRT equations for each trip. And there's going to be unknown things about each trip. And you can even do this with a table. The key with doing these is just being really, really clear about what you're putting into the table and what you're setting up as your unknown. So let's try example 6. I'm just going to do the exact example. So this is example 6 from the book. This is on page 524. So we have a Vermont freight train with logs leaves Boston heading to Washington, D.C. at 60 kilometers per hour. So, so I'm going to draw a train here and a train here. Or this is Boston. This is Boston. This is DC. And so the first train leaves, train 1, it leaves at 60 kilometers per hour. And train 2 also leaves from Boston. It goes faster though, it goes 90 kilometers per hour. But it leaves 2 hours later. And I'm not writing out the full problem. I'm just kind of drawing a little schematic so I can kind of visualize what's happening. So the train 1 has a head start. The question is, and let me make this a little bit prettier. The question is, at what point will train 1, or train 2 rather, the later one, catch train 1? Okay, so what's the distance at what distance would they catch? At what point will train 2, what distance from Boston will train 2 catch train 1? So let me kind of rephrase that here. All right. Yes. Can everyone see the problem here? Okay. So let's start off with what we know. And this is one approach to do it. It's a very good approach. It's kind of like if you ever have one of these traveling problems where things meet, or if they have to go back and forth or something, you can generally always apply this idea. So let's start off with a table here. And we're just going to fill in the table to get our equations. That's all. So we have trip 1, and we have trip 2. And because we're going to only have and for each trip, we're going to write in our table distance, a column for distance, a column for rate, and a column for time. And technically, before you kind of have any information at all to begin with, you actually have 6 unknowns. Distance 1, and you can write a little subscript for whatever unknown. DD1, R1, T1, D2, R2, T2, because there could be 2 different trips. But you want to use the information in the problem to fill in as many of the squares as you can. And there's another aspect that's really important. You want to kind of decide, what am I looking for? And how can that help me reduce the number of unknowns? Do I really need, for example, 2 different times? Do I need 2 different rates or stuff like that? So let's just start off with what we know. Can anyone tell me what can we plug in for trip 1? Nice, we have the rate, right? We know 60 kilometers per hour. So I'm just going to put in the rate as 60. What else do we know? Do we know the distance traveled? No. So if we don't know that, let's just write D. And technically, I'm going to write D sub 1. But I'm going to try to make sure that I don't use another. I don't want to use too many unknowns. But it's technically like the first distance is unknown. What about the time? Do I know the time? Well, we don't know the time. We just know the other train leaves a little bit later, right? So we don't quite know the time. So I'm going to put another variable there. I'm going to put T1 in here. And I'm putting the 1 just to say it's related to trip 1. I don't know what it is. I have no information about it. Okay. So the next step is the one that you have to kind of think about the situation to see if you need to actually use new variables, or if you can relate the variables, if you can use instead the previous variables. Okay, so for trip 2, what do we know right away? What's something we can plug in without hesitating? 90. We know we're given the rate is 90. Okay, technically the distance is D2 and the time is T2, but that would give us 4 unknowns and 2 equations, which would just be way too many unknowns. Do we need to really plug in a different distance for the second trip? Why or why not? What are we looking for? Lupe, why not?
I don't think so, because we're just going to find the one point in which they both meet.
Exactly. So when they meet, and you'll start to kind of see these patterns with these types of problems. Whenever you see that 2 trains leave from the same spot and have to catch up to each other, that means that when they meet up, their distances are the same. So instead of using d2 as another unknown, d2 actually equals d1. So I'm just going to write in here d1 because we're looking for d2 equal to d1 where they meet after traveling from the same starting point. Thank you, Lupe. Very good. There is another version of this problem where trains leave different locations at different times, and then it's like, and we know how far apart they are, and it's like, where do they meet? Like, where do they collide or whatever, or where do they pass each other? That one is slightly different than this because the distances traveled are not exactly the same, but there's still a nice relation, and we'll do that one later. Okay, what about the time? What does it mean? Do we need to really write in T2 and make a whole new variable, or can we use the information that they give us to somehow instead use T1? Nice, Savannah. Can you say what you wrote there?
I said T1 minus 2
Yeah, and how do you justify that?
because the second train left 2 hours after the first.
Awesome. And so it was on the road, on the train tracks for less time, right?
Yeah.
Perfect. Okay. All right, that's it. We have our table. And now, and I think this table, like once you kind of recognize these strategies or these situations, this table is a very nice systematic way to approach them. And now you can just set it up as a system. We have a system of two equations. We have D1, and I'm just going to drop D1 and T1. I'm just going to do D and T, but you know it comes from the original from the table. So D equals 60 times T, and D is also equal to 90 times T minus 2. When equation is written like this, which approach would you like to use?
I think substitution.
Yeah, nice. Yeah, I would probably use substitution. Elimination also works fine. Either approach always works. But in particular for these types of problems, if you get the distances are equal, just solve for the time by setting the two equations equal to each other. So we can write, do substitution, and we can write 60t equals 90 times t minus 2. Oops, not t minus t, that's t minus 2. And then we can expand this. We get 90t minus 180 equals 60t. Rearrange this, we get 30t equals 180, or t is equal to 6. So we have 6 hours. Therefore, plugging into the original one, we know that the distance traveled would be 360 miles. Okay. Let's see, third miles. Let me see here. Okay, so this is a good place to stop. I'll encourage you to think about this problem and see if you can solve it in any other way. There's sometimes nice approaches with these problems, similar to that one we did with the credits, that allow you to solve it without really doing any algebra at all if you think about things in the correct frame of reference. For example, you guys know that when you're on the highway and you're traveling at 60 miles per hour, and somebody is coming up behind you really, really fast at 80 miles per hour, what does it look like that car is doing from your perspective? How fast does it look to you like that car is going if you're in the highway at 60? Well, if they pass you it does look like it's going fast, But imagine like you guys know the like the Matrix movie or where like everything around you is like a white background, so you don't actually see the road. You just know that you're going at 60. How fast does this actually seem that the car is going past you? You're going at 60, they passed you at 80. It seems like they're going 20 miles per hour faster than you. So sometimes changing your frame of reference can make these problems actually like a lot easier to solve without doing any of this system stuff. I want you to do this because it's important and it helps you to feel confident, and it's a really good approach. But as a challenge tonight, see if you can come up with a different alternative solution, similar to how in the first problem we did it with the credits. There was a kind of sneaky way to do that. Are there any questions with this setup and this answer? Okay, no questions, great. I'm really proud of you guys. I think you did an awesome job on the first two. A lot of people didn't know how to do those problems in the beginning. Like I remember like 8 people right away said, I'm stuck. And then I kind of happy that I asked you to think more about it, and I knew that you guys could do it. And I hope that you now feel that you can do problems that you haven't seen before. And that's, you know, it's scary. It's like, doesn't feel like most usually how we're taught how to do math, but I think it's really valuable. I'll see you guys on Thursday. I'm also going to post some problems later tonight from this chapter so you can kind of practice these ideas. And don't be scared if you don't know how to do a problem. It's actually fun to think about something that you don't know how to do for a little while. That's a good thing. All right, guys, have a good rest of your day, and well done.
Thank you.
Bye.